So there's two things I really like about math, at least two things, but two of my favorite things are, one, the certainty that comes along with math, the kind of certainty that you get with mathematical theorems, mathematical proofs, mathematical solutions, all that. It really is, it's unsurpassed in terms of just the pure certainty that comes along with mathematical conclusions. Even the conclusions in the other sciences don't have the same sort of logical, just couldn't be any other way about itness that mathematical conclusions have. But the second thing I like about mathematics, maybe even more than the certainty, is the surprising nature of the connections that come out as you do mathematics, the connections you see between things that might not seem initially very connected at all. And I have an example that I'm going to share with you that I think illustrates this point, especially the surprisingness part of it, and I'll leave some of the certainty for you to fill in, although it's there. But it's all about this function right here, f of x here, this kind of ugly multi-line function. It's x squared if x is between 1 and 2, but if x is between 2 and 4, we compute x squared over 4. And so that's our function. This function, it's a piecewise function, a conditional function. You've seen them in calculus probably if you've had that. Here is the graph of the function. It's between 1 and 2, it's the parabola y equal x squared, and between 2 and 4, it's another parabola, y equal x squared over 4, a more shallow parabola. But there it is. And I'm only interested in x values between 1 and 4. One reason is that because if I take an x value between 1 and 4 and apply f to it, I'm going to get a value between 1 and 4. If you think about it for a second, you see why that's true. I mean, x squared is always between 1 and 4 if x is between 1 and 2. And x squared over 4 if x is between 2 and 4 turns out to always be between 2 and 4 itself. So that's our function. And what I'm going to do, I'm going to play a little game with it. I'm going to just start with an x value, say somewhere between 1 and 4. Let's just say x equal 3. And I'm going to apply f to it and see what I get. And I'm just going to do that over and over and over again, and that's what my table here is set up to do. So my first x value is going to be 3 here. And what I'm going to do is just apply f and continually write down the result and see what happens. But for each x value, I'm also going to sort of write down a code. And the way I'm going to do the code is very simple. If my x value is between 1 and 2, in other words, if I'm using the first line of the function, I'm going to write down a 0. But if my x value is between 2 and 4, in other words, if I'm using the second line of the function, I'm going to write down a 1. So I'm going to keep track of those codes and the x values that generate them as we go. So, for instance, my first x value is 3, so that's between 2 and 4, so I'll write down the code 1. And now I'll compute f of x. Now f of x would be our x squared over 4 in this case, so I've got my trusty TI to help me with all these difficult calculations here. So it turns out that if x is 3, then f of x is 9 over 4, which is 2.25 according to the TI. So I'll write that down here. That's my new x value, and I ask again, is that between 1 and 2, or is it between 2 and 4? It's between 2 and 4, so I'm going to write down a 1 again. And then I just keep doing this over and over. So x is 2.25, and I apply f of x again, and this time I'm going to get 1.265625 according to the TI. Let me just round that to 2 decimal places, so that's about 1.27. And I'll let the TI, of course, keep up with all the digits. That, I again ask, is that between 1 and 2 or 2 and 4? Now it's 1 and 2, right? So the code is a 0. So I just keep on doing this, and it's a lot of fun. I'll just sort of cut to the chase here. The next value is going to be 1.60, so that the code is a 0. The next value is 2.57, so that's a code of 1, and so on. So let me just fill in the table here. 1.65, that'll be a code of 0. 2.71, that'll be a code of 1. 1.83, that'll be a code of 0. 3.36, it's a code of 1. 2.83, that's a code of 1. 2.00, so that's going to be a code of 1. And then 1.00, so that's a code of 0. And we could go on all day, but we got nothing, right? Well, actually, we haven't. I want to look at the code now, and I want to think about it in a certain way. I've got 1, 1, 0, 0. What I'm going to do is I'm going to think of this as a number, the whole code as a number written in binary, and with the decimal place after the first digit. So I want to think of this as 1.10010111110. So that binary number right there, that binary decimal, 1.10010101110, and there's a lot more digits out there that we didn't compute just because we were having too much fun. But what number is that? Well, it's in binary, right? So this really means this is the ones place, so this is 1, and then plus 1/2, and then plus 0 times a fourth, plus 0 times an eighth, plus 1 times a 16th. Let me write this down so I can add it up on the TI. That would be my 1/2, no a fourths, no 1/8, but a 1/16th, no 1 over 32, but I get a 1 over 64. 128 is left out, but this would be 1 over 256, 1 over 512, and 1 over 1024. So I can add those numbers up and actually see what binary number this thing represents. And so let me do that. 1 plus 1/2 plus 1/16 plus 1/64 plus 1 over 256 plus 1 over 512 plus 1 over 1024, and we'll have to be satisfied with that, even though there's a lot more decimal places after that. I get this number. In binary, this thing is going to be equal to about 1.584960 ... Okay, so that's the outcome. That number 1.584960 ... And there's some left out precision here because we could have carried this on for as long as we wanted to. But I want to think about this number for a second. What I want to do is take 2 and raise it to this power. So again, the trusty TI helps me. 2 raised to that answer power, and see what I get. And here, I'll show you exactly what I got. Can you see that? Maybe. Look at that. 2.99999, lots of nines, and then some stuff. So if you've had calculus, what do you think the limit would be as we continue this process out forever? Looks like it would be 3, right? 2 to this number looks like it's going to be 3, the very first number we started with. That says that this number, if I had allowed myself to have an infinite amount of fun by computing all these ones and zeros, is the log base 2 of my starting point, which is 3. Why should that be? That's kind of amazing. Well, actually, you can figure out why that should be without too much trouble. If you just think about what this function would do to an x value in binary. So it is actually the case that no matter what number you start with, if you play this game, you will get a sequence of ones and zeros when which when interpreted as a binary number is going to be the log base 2 of your starting point. So I think that's kind of amazing. It's one of those connections that you wouldn't think would be there. You certainly, I mean, even after you see it, it's like, why would it be there? Why would it be like that? It is like that. It's kind of amazing that it is, and it's one of those charming aspects of mathematics that keeps us mathematicians gainfully employed and happy. So we'll, in our next episode, we'll revisit this and try to figure out why it is that this rather ungainly ugly duckling of a function, when iterated this way, produces a sequence of digits that's actually the log base 2 of the starting point. So see you back here later.